Hello everyone and welcome back. It is time for another demo. This time it is PIM Dense-Mode on iOS routers. So without further ado, let's begin. Here is our topology that would be used. This is the same topology we've been using throughout this particular lecture series. Couple of things that I want to make sure everybody understands right now. R7 in this particular topology actually is up. So R7 is a functioning router in our topology. Also, all of the links are of equal speed. So every single link is a gigabit Ethernet link. And all of those links are actually being used as sub-interfaces. So for right now, for this very simple demo and the very first demo, there is no troubleshooting really built in. We'll just see the natural behavior of PIM Dense-Mode, and therefore all of the links are of equal speeds. Later on in the series, as we go through the troubleshooting problems, I may change the speeds of these links, and that's why R7 is in a different color. So R7 would always be the outlier, but right here it might as well be orange because it's exactly the same as the other routers. Also, there is OSPF on this topology which is working, so you have end-to-end connectivity. The source can actually reach the receivers and vice versa. Apart from that, there is no PIM enabled anywhere here other than on the southbound interfaces on R5 and R6. So remember from our IGMP demos? On R5 and R6 on Cisco routers, to get IGMP going, we actually had to have PIM enabled on it. So there is PIM Dense-Mode here and PIM Dense-Mode here as well. And that's just to facilitate IGMP. Now there are no IGMP groups, so whatever IGMP groups that Rec 100 and Rec 200 had joined, we have actually made them unjoin those groups. So we issued the right commands to make sure that they're no longer subscribing to those groups. That means there is no source in this topology, there is no IP multicast routing in this topology, plus there is no PIM anywhere, and there are no groups that any of the receivers have joined. So it's basically just working at a unicast level right now. So let's go ahead and ascertain a couple of things. One of the things I'm going to do is make sure my source can reach both Rec 100 and Rec 200. So I'll say do ping 172.26.56.100 to make sure that goes, and 200. And it looks like there may be some problem with 200 there. So let's go ahead and quickly figure that out. So Rec 200 is right here. Let's look at the interface, and the interface itself is down. So let's bring that interface back up. No shut. And once it comes back up, hopefully there will be communication here. So there we go. We have end-to-end connectivity. Let's run a couple of traces to both of those routers. So 2656.100. Or would it be do trace? So there we go. We can actually see it goes through router 1, router 2, router 3, router 4, then goes over to router 6, and then finally it reaches the destination. How about 200? Probably around the same path. It actually goes through router 5. So we can actually see, and this one actually does go through router 7. So they are using two very different paths here. And that's a good thing. So they're using two different paths. And if you were to see, if I was to actually look at this, so to Rec 100, I'm actually using 1, 2, 3, 4, 6, and 100. So the traffic actually comes from R1. I'm sorry, from the source to R1, and then it's R2, R3, R4, R6 to R2 to R3 to R4, then goes over to R6, and then finally to Rec 100 here. Now for the other receiver, Rec 200, it is 274 and then 5. So it's a completely different path, but these are all equal cost paths. So from R2, it goes over to R7, to R4, this time to R5, and then to 200. So they're very diverse paths, and I'm pretty happy about that because we have just now made sure that all of our links are working. OSPF is working on all of those links. So now it's time to actually go ahead and configure multicast routing everywhere. Now, multicast routing will be on all of the routers in the topology. So from R1 to R7, every single router would have multicast routing. Also, every single one of these interfaces, including the interfaces that go towards the sources and towards the receivers, they also need to be running PIM, and they should also be running the same mode that is running throughout the topology. So for our topology, that is going to be dense mode. So we will run dense mode everywhere, and it's important that we actually run dense mode on these edge interfaces or the leaf interfaces. So facing the receivers, facing the sources, and that's how the routers actually know where it's connected to, basically the edge of the topology. So the very first thing to do on Cisco routers is to actually issue the IP multicast routing command. So IP multicast routing is not working by default, and it has to really be turned on. So if you go to a router and say something like do show IPM route and see nothing there, nothing at all, no groups of any kind, that is a pretty good idea that multicast forwarding is not enabled. So one of the first things you have to do on Cisco routers is to enable IP multicast routing. And this would be the same command that goes everywhere, IP multicast routing. And now if I say do show IPM route, it doesn't show me that message. Plus well, there's no PIM right now, but it at least does not show me this message. So right now what it tells me though, because the table is completely empty, that there is no PIM running on this topology. So if I was to say do show run include PIM, you can see there is no PIM running, and that's why the multicast routing table looks fairly empty here, and actually is completely empty. So the next thing to do, well, first we have to put this command everywhere, right? So this command has to go on all of the routers. So let's go ahead on R2, R3, R4, R5, R6, and R7. Those are all of the routers that are going to need IP multicast routing command. The next thing to do here is to enable those PIM dense mode interfaces. So I'll give a couple of examples. If these red were PIM-DM interfaces, then all of these interfaces on every single router, so every single router in our topology is PIM dense mode enabled. There are no exceptions. So other than the loopbacks, all of the connected links are all PIM dense mode enabled, every single one of them. So that actually takes a bit of doing. So we'll go ahead and make sure that every single one of these interfaces actually has PIM dense mode enabled on it. So on R1, that's going to be interfaces do show IP ID brief. That's going to be interfaces G01 and 12. So INT G01, IP PIM dense mode. Also on 12, IP PIM dense mode. Then we continue from there, do show IP ID brief. I'll do a couple of these and then I'll pause the video while I get the rest of the topology up. But INT G00.12, IP PIM dense mode. Then you get to 23 dense mode, then you get to 27 dense mode. I'll pause the video now while I get the rest of the topology up, and then we will find a simple way of actually testing if there is PIM enabled throughout the topology. So I'm back and I have enabled IP PIM dense mode on all of those identified interfaces. Now there are several different ways of doing this. I could do basically a show command that I send to every session. I could say something like do show run include interface and then IP PIM dense. And if I look everywhere, you'll see that I have all of these interfaces now enabled with PIM dense mode. But there's another simple command that can be done. It should be ideally done from one of the edge routers to one of the edge routers. And instead of trace, you would say mtrace. We will cover mtrace in a lot of detail in one of the upcoming lectures, but for right now, for quick verification, mtrace literally traces out the multicast path throughout a topology. Now, it actually works on the source, so the IP unicast source. So in this case, I am on R6, and I'm actually going to trace, I'm on R6 here, and I'm actually going to trace to the actual source, which is 172.26.1.10, which is up here. So 172.26 1.10, and it essentially tells me what are the hops that the path is actually taking. So this would be the multicast reverse forwarding path. It goes from 6 to 4 to 7. So, and 4 actually basically has 2 routes to it. So nope, so 4 goes to 47.4, which is router 7. Router 7 goes to router 2, router 2 goes to router 1, and router 1 is directly connected to the source. But as long as you see PIM on all of these interfaces, you're golden. There's really no problem there. So for example, if I was to go to R2, and the link that's connecting to R1, which is G0012, so if I was to go to that link, and I say no IP PIM Dense-Mode, now if I run that trace again, it should actually show me some problems. So there we go. R2 doesn't even have a route. So it doesn't have a multicast route that takes it to that particular source. How about if R2 had IP PIM Dense-Mode, but IP multicast forwarding was not enabled here? No IP multicast routing. Now what happens to that mtrace? So the mtrace is now good. All of the interfaces are PIM enabled, but here on router 2, multicast itself is disabled. So mtrace is a good quick command to verify these initial connectivity things, and we'll be covering this in a lot more detail. There is much more detail to be discussed about mtrace, which it essentially needs a video of its own. But for right now, everything is good to go. Next thing I want to see is if there are any receivers that have been inadvertently left up in my topology. So on R5, I'll say do show IP IGMP groups. And like I said, this 224.0.140, that's by default on every single one of the routers. So if I say do show IP IGMP group on all of the routers, I'll see every router is sort of subscribed to this group, and you're going to be your own reporter as well. So don't pay any attention to it yet. It's for a feature called Auto RP, which will be discussed after we have covered sparse mode. But for right now, anytime you see this, this is normal. But that doesn't really mean that we have explicitly joined the group. If you look at the last reporter, it's the router itself. So the router itself is joining that group. So don't worry about that just yet. And as you can see on R5 and R6, there are no external groups that have been signaled from the receivers. So right now we are actually going to bring a source online. And how do you bring a source online? So from our previous lecture on source signaling, it's pretty simple. The source has to send a multicast packet, and it has to be received on a multicast enabled interface. So as long as that interface is dense mode, sparse mode, or whatever, that source tree has now been signaled. So the source has now signaled that there is something active. This is, remember, so this would be the S, comma G. Because where are you getting the G? The G is coming right from this multicast group, and the source IP is the source IP of that packet. So just by using that packet, now R1 or the FHR knows about the S, G, and it's going to actually create that. So let's go ahead and quickly quickly send some traffic over from the source and see what happens to our domain. So we'll say ping, and let me just get out into the exec mode here. I'll say ping 239.111. Why not, right? So that's a group that nobody should be responding to. And let me send just a single packet. So one single packet goes out. What we want to see is on the FHR, or the first hop router, what happens to the multicast routing table. So I'll say show IP, do show IP mroute. And there we go. There is the S, G right here. So the S, G has been created. There's a lot more to discuss with it. But for right now, we know that an S, G has actually been created. And that's a good thing. Now, this should also be, this traffic is dense mode traffic, right? So if you look at, and we'll go over the flags, but if you look at this D flag, this means it is the dense flag. And that means this group should be flooded throughout the domain. So that means all of the other routers from wherever the dense mode path took place, all of the other routers should also know about this group. So I'll actually send the command do show IP mroute. And actually, let me just bring this one in. So I'll say do show IP mroute 239.1.1.1. So I'll qualify it with the group, so the output is not so verbose. But on R1 there is an entry, R2 has an entry, R3, R4, R5, and you get the idea. All of these routers now know about this group, because what happened? As the traffic came in, because it is dense mode traffic, it was actually flooded to all parts of the network. So it was flooded from R1 to R2. R2 should have sent a copy down here, down to R7. R7 should send a copy over there, R3. And you get the idea. Everybody got a copy of that traffic, and ultimately they were able to create that S, G state. So let's go back to our first hop router and actually figure out what was done in response to this traffic. Now, one of the main things that trips people up a lot with the dense mode implementation in iOS routers is the star, G entry. So if we go back to the lectures on the multicast routing protocol and multicast routers, star, G, or any source multicast, this is really a shared tree, right? So this is what PIM calls rendezvous point tree or shared tree. A shared tree should not really exist in dense mode. This is dense mode, so you're only working off of SPTs, shortest path trees. And those are these S, G trees. So what is this star, G tree doing here? Well, to make the answer very succinct, it is just a multicast routing table optimization that has been used. It provides you, so this particular entry here, it provides you with some of the important information about this particular group. So 239.1.1.1, let's see what information can we derive about this group. So number one, it is a dense mode group. If you want to know if a group is dense mode or sparse mode, this entry would actually tell you that this is a dense mode group. The next thing that, because this is the first hop router, it's only connected to one other neighbor. If you look at the OIL or the outgoing interface list, it should have all of the interfaces that are connected to other PIM neighbors. So all of the PIM neighbors connected to this router should be in the outgoing interface list. So essentially you need to flood to all of those neighbors. And because you need to flood the traffic to all of those neighbors are now gathered in the outgoing interface list. This list down here on the shortest path tree is going to be a subset of this list up here. So all of the qualifying interfaces from the star, G, which is the collection of all of the interfaces, is going to make it to the S, G. And that's what's going on with the star comma G. So star comma G is in dense mode is going to provide you some important information in Cisco routers, but don't get thrown off by it. It's not really being used for anything. What is being used really is the S comma G. So let's take a look at the S comma G. The S comma G similarly is going to give you information. Well, the very first parts here are pretty easy, right? So it tells you about the source. It tells you about the group. So S comma G right here. It also tells you about some other information about this actual group and its treatment right here. So if you look at the flags are P and T. And if you look up here, so always look at the flags themselves. They are going to be very important, especially when you are troubleshooting. So when you look at the flags, they are P and T. There we go, P and T. And P means that the group is pruned, which sort of makes sense, right? So you should have flooded out all of the traffic, and then the traffic should have gotten pruned back from the LHRs back to the FHR. So it makes sense that this group is completely pruned. There are no receivers in this group. So that's why it is pruned. T stands for, and I cannot locate T here. It should literally just be the shortest path tree, but I am having a hard time looking at it here. So T, right here. So that should have been easy, but the SPT bit is it. That means it is literally just on the shortest path tree, which makes sense. It's an S comma G entry, so it makes sense that it is on on the shortest path tree. Now for the incoming interface. Remember, one interface is always going to be the IIF, or the incoming interface. In this case, well, it makes sense. It is the interface that is connected to my source, sort of directly. It's on the same LAN. So G00.1, that becomes my interface. Now the RPF neighbor is going to be very important. So RPF neighbor is the next field here. An RPF neighbor usually identifies the upstream neighbor. Well, in this case, the source is directly connected to me, right? So the RPF neighbor is just me. I'm originating that source. So 0000 usually would identify either a problem or that the router is an FHR. So that is what that RPF neighbor there is identifying. Now, finally, you have an outgoing interface list. It's a list of 1, and it is a directly connected dense mode neighbor. So this is a directly connected dense mode neighbor, and that means, and the state of it, so it is dense mode, and it has also been pruned, which makes sense because you should have gotten a pruned request, and the interface itself should have been pruned. Now, one thing that I neglected to do was to show you the PIM neighbors command. So let's go ahead and quickly look at the do show IP PIM neighbors command. So all of these routers should be neighbors on their respective interfaces. So as you can see, R1 is a neighbor with R2. R2 it has neighborships with R1, R7, and R3. And so on and so forth. So you would see that the neighbors are coming up. Now, one of the most important things, this relationship does not tell you whether it's a sparse mode relationship or a dense mode relationship. So if I go back to, say, R2, R2 has a bunch of neighbors. All it tells me is R2 is the DR on this particular link, so on G0023. Now remember, it's a point-to-point link, but PIM is treating it as a multi-access interface, so that's why there is a DR election here. PIM dense mode itself does not require a DR election, but on multi-access, remember IGMP version 1 may need to use this as a designated querier, so it's built into the protocol. It also tells you, well, it tells you the number of neighbors. Oh, I'm sorry, the DR priority. So I've not changed the DR priority. By default, we'll do that in sparse mode. So it should have been the highest IP that won. Actually, this is telling me that 172.26.23.3 is a DR, which makes sense because if everybody has equal DR priorities, then 23.3 versus 23.2, 23.3 should be the DR, which it is. It also tells me, so remember in the hello option, there should have been that state refresh option that was selected. So it tells me that in 172.26.23.3's hello messages, I do see the state refresh option enabled. So it is state refresh capable. Other than that, proxy capable, I'm actually forgetting what that is. I'm pretty sure it's not very important. And the generation ID to help across restarts. So we talked about the generation ID in the PIM Dense-Mode lecture. Let's quickly take a look at one of these hello messages and what those options really look like. So this is just a certain hello message. It's coming from 56.5. If I go further down, I should also see, well, I could say just PIM. And here's a message going from 12.2 out on one of the interfaces, which is 12. So this is going between R1 and R2. And if you look at the PIM options, there are 5 PIM options. There's the hold time that is carried basically to see how long R1 is going to wait for R2. The generation ID, which should change across restarts. The DR priority. And the state refresh capable information option, so that they tell each other that yes, we can perform state refresh, which we'll see a demo later. This last option, I'm pretty sure is that proxy option. I'm not exactly sure what it does. I've never used it, so maybe we'll do some research and I'll do another lesson on it. But right now, the other 3 are more important. Well, back to the case at hand, which was looking at the dense mode routing table. So right now, if I look at the show IP mroute, I'm pretty sure I would see nothing. Group 239.111 not found. That is because my source sent a single ping and then it died down. So it sent no more pings after that. There was just a single ping sent right here. And after that, the source went quiet. That means the first hop router stopped receiving all of the packets, so there were no packets from the source. And after a while, if you don't receive any data, that data coming in, so that data coming in on this interface right here, between R1 and the source, this constant data, as long as it keeps coming in, it keeps the state on R1 refreshed. And that means that R1 can then keep the state on the rest of the network. But if this traffic stops, then R1 expires that state ultimately and it expunges it from the multicast routing table. It's not going to keep it there indefinitely. And if you remember, that number was about 3 minutes or so. So after 3 minutes, it's going to get rid of that state. So let's generate a few more packets. In fact, what I'm going to do this time is that I'm going to just send continuous packets. So I'll say 239.1.1.1 and I'll say timeout 1 so that the packets are sent a little bit faster. And I'll tell it to repeat for the highest amount of time or the highest repeat count. So now the source is completely active in our topology. That means the states on the multicast routing tables should not die out. So now if I look at the show IP mroute, I should actually see the states are back. And now we can actually look at the timers of these states. So from this point on, all I'm going to look at is the S,G entry. The star,G entry, as you see, it has its use, but really apart from telling a couple of things, it's not really going to be used that much. Now I can see there are 2 separate timers. So there are timers that are associated with the group itself. So this is the timer that is associated with the group. And it tells me how long has this source been active for. So it has now been active for 11 seconds. You saw the very first packet 11 seconds ago, and that's when you declared the source to be up. And how soon, if I do not get a refresh, how soon am I going to expire the state? So this is the expiration time. So that actually is the expiration time of this prune. So I'm going to actually move the packet. So right now, the whole state is in prune. And as this expiration timer expires, I'm going to move it from prune back to forward, and I'm going to repeat my flooding behavior again. So that's what that timer means. There is going to be a separate timer associated with each of the interfaces. Now in my case, it's a single-legged router. It's just got one interface into the multicast domain. That means these two timers are going to be very close to each other. So 248, 249, as you can see, they're very, very close to each other. So let's take a look at this again. And let's see if those timers have changed any. So now you can see the timer's gone all the way down to 56. And this timer's gone all the way down to 57, and that uptime keeps increasing. So as long as there is a steady state of traffic, I'm just expiring that prune time here. So that timer is going to expire, and at the expiration of that timer, I'll reflood the domain. Let's look at one of the middle hop routers. Let's look at R4, because R4 definitely has to be on the tree. There's no way, whether the traffic comes through R7 or R3, there's no way that R4 is not going to be on that tree. So let's take a look at do show IPM route on R4, and actually do show IPM route 239.1.1.1. And once again, this time the star comma G actually has a much richer outgoing interface list. And that's really because if you look at R4, it has 4 neighbors. So R4 actually has 1, 2, 3, and 4 neighbors. So it has 1, 2, 3, and 4 neighbors. So it makes sense that it has 4 separate interfaces in the outgoing interface list. So that makes a lot more sense, I hope, on this particular router. But again, like I said, we're more interested in the S comma G always. And in this S comma G, you see that there is the S comma G again with the timer. So there is an active time, there is an expiration time, the whole group is still pruned. This time the RPF neighbor is different. So the RPF neighbor now is going to be the route that you selected to go back to this source. So basically the router is doing a routing lookup on 172.26.1.10. And it's picking up out of all of the resultant routers, so there is ECMP happening here. It's essentially picking the highest IP right now. So I'm not using multicast load splitting right now. We'll use that separately, maybe in sparse mode or sometime. But right now, out of all of the available RPF neighbors, the one with the highest IP is going to be chosen as the RPF neighbor. So if I look here, if I say do show IP route, so just to show IP route in 172.26.1.10, I have 2 ways to get there. So I have 47.7, that's the neighbor to my left, which is R7, and 34.3, which is the neighbor above me, so R3. Now, out of these, it's very easy to say 47.7 is a greater number than 34.3. So that is being used as the RPF neighbor. If you're ever in doubt, you can always use the do show IP RPF command. And you would use this command on a unicast source IP. So that is something that throws a lot of people off. But remember, the reverse path forwarding check is towards the source, not the destination. We don't do destinations. Well, I mean, yeah, we send packets over to the destinations in multicast, but we are essentially trying to route packets or forward packets away from the source on the reverse path. So the reverse path is to the source, right? Reverse. So this would be on 172.26.1.10. And there you go. This is my RPF neighbor. Now, a lot of times the question comes up, what is this question mark? This question mark essentially is just the DNS entry. So if I actually was able to resolve the DNS address for 172.26.47.7, then I would actually see a name here. So just to prove a point here, I can say IP host, and then R7. And I can put an IP address there, which would be 172.26.47.7. I may need to use one more command here, but let's look at that do show IP RPF. And now you can see the question mark is gone and it's just R7. So that question somehow creeps up all the time, but this is essentially what it's for. So anytime in multicast verification commands you see a question mark, it's a pretty decent guess that it's probably has to do with the named resolution. So as long as you have named resolution, then that's what would happen. But right now, highest IP wins. So on R4, let's look at that show IPM route again. The timers should have changed. So now look at that uptime. And once again, I'm going to qualify it with 239.111. And look at that. Well, the uptime is back. So actually, this is not the uptime. I believe this is the time since the last refresh. And that's actually what it is. So this is how long ago the router was refreshed. For the total uptime, that would be up here. So if you're looking at the total uptime for the whole group or per interface, that's up here. So this is the total uptime in the star comma G entry. And this here is the time since last refresh and time till next refresh. So right now they're just split across the middle, but as you can see, one of them keeps going up, the other one keeps coming down. But what is happening every 3 minutes? Every 3 minutes, this prune entry on every interface is moved to forward. So once it's moved to forward, traffic starts flowing again through the entire domain, and then everybody has to prune back. We know this through our lecture. So what we should be seeing here, if I was to look at the packet captures, and I say ICMP, and let me also filter on PIM messages of the type prune, or actually equal to prune. So I'm looking at prune messages. Actually, let me try to find out what that filter really is. So I had to actually go by the PIM type of 3. It looks like Wireshark doesn't really have a join prune message filter, but anyway, we are filtering on the join prune message. We're filtering on ICMP requests. And I'm actually taking the VLAN ID into consideration because this very first hop router here, it's a native interface. So I'm basically, there's constant ICMP traffic on it, which I don't want to see. So I'm essentially eliminating that with the VLAN ID command. Well, this is what is happening in the steady state of our network. The echoes come in and then they're flooded throughout the domain. So if you look at the VLAN IDs here, those VLAN IDs are changing, right? So this is a packet capture that is running on the entire network. So if you look at this, all of the VLAN IDs here are different. Right here. So 23, 27, 24. As a response to that, as a response to this flooding, then the join and prunes go up. So the joins and prunes then go up, and then this process repeats, and it should be repeating every 3 minutes. So let's take a quick look at that, if this process is actually taking 3 minutes. And if you look at this 1501, actually I have the time in reverse, but so 1327 then happened at 7:15. And then happened at 5:33. So whatever that amount of time is, that should be around 3 minutes or so. So this should be actually this way. And going down and over again. You see the packets flooding over and over again, and then the join prune messages sent hop by hop for every single one of those floodings. So right now, this is the steady state of our network. Flood every 3 minutes, prune back every 3 minutes, flood every 3 minutes, then prune back every 3 minutes. And that's how it happens. So what are these prunes for? So let's take a look at one of these actual prunes. So we know it should be a prune, it shouldn't be a join. It's protocol independent multicast. It's 224.0.0.3, so it's going to that destination IP. It should also be a TTL of 1. So right now it's a TTL of 1. And then in the actual PIM, there is a group that is identified. That looks like our group, 239.111. Remember, the number of joins is going to be 0. We are not trying to join any groups. We are actually trying to prune a group. And that S, G then results into 172.26.1.10/32. And that's going to happen at every hop over and over again. So now, right now the prunes are in the topology because there are no receivers. So remember, that's one of the first reasons why there is a prune, because the leaf routers could not really find any valid receivers. Once we do get the receivers though, we should start the traffic flowing. So let's go ahead on one of the receivers, rec 100, and I'm going to join that group. So on this interface, I'm going to say IP IGMP join group 239.1.1.1. Once I join that group, the source should actually start receiving unicast replies from me. Now, the reason for this is because everybody had the steady state, what should have happened here, and we'll see it on the packet capture in a second here, we should have had, so if blue is IGMP and then PIM is red, what should have happened here is 100 should have sent a membership report out. And once that membership report went out, R5 and R6 should have sent, I'm sorry, this should be blue. So the report went out for that group. And once that report went out, R5 and R6 should have grafted themselves back onto the network. So they should have grafted, they should have gotten a Graft-Ack back, and then the grafting process, actually it's happening this way, should have happened all over the place. So let's go ahead and take a look at if this grafting has actually happened here. So back to my packet capture here. And this time the PIM type is going to be, well, none of the names are actually working for me today, somehow. There we go. There are the PIM graphs. So for some reason, wouldn't take it in that complex expression. But if you can see, 6 and 5 both sent it to R4. So this is going from R6 and R5 to R4. R4 is sending it to R7. R7 then had to graft itself back to R2. R2 had to graft itself back to R1. And both of these should have also been replied by Graft-Acks. So there we go, graft, then Graft-Ack, another graft, Graft-Ack, graft, Graft-Ack, and the traffic now starts flowing because all of those interfaces that were pruned before, so for example, on R1, all of these interfaces were pruned. Some of these should now move into forwarding. So there should be one, but some of these should now be forwarding. And actually, if you look at it, R6, so R4 and R6 is the one that is now forwarding. So it is constantly forwarding, and it's not being pruned anymore because there was a grafting request that came from router 6 and it was accepted, and then router 4 in addition grafted itself back to router 7. So if I go to router 7 and I say do show IP mroute 239.1.1.1, I should see that I have now grafted myself back. So R4 has now grafted itself back to R7. R7 should do that to R2 and R1, and now the traffic is flowing throughout the domain. So that prune flag is now gone from this group because there is at least one interface. So it's more apparent on R4. The prune flag is gone, not because there are not any prune interfaces. That's because there are not all prune interfaces. So that P flag would appear here if all of these interfaces were pruned. Right now, only 2 out of these are actually pruned. The other one is in forward, so there is no reason to prune the group. The group as a whole is not pruned right now. So that is what is really going on here right now. Now so we've covered the flooding and we have covered the actual pruning back. So we flood the packets out, we prune back, and then if in case we need to graft, we actually graft ourselves onto the group. The last hop routers. So now we've talked about the pruning and we've talked about the flooding. So it's now time to talk about PIM assertion. So remember, there is still that case of assert. And one of the cases here would be, so as the IGMP request came in, remember it came into both R5 and R6, yet R4 is only forwarding data out to R6. So if you look here, R4 has only moved R6 into forwarding. That means something must have happened in the middle that caused R5 to go back into prune. Because as we saw, both R5 out here, so both R5 and R6 sent that graft message. They both grafted themselves onto R4, yet we see that R4 has moved R5 back into prune. So what must have happened? Well, what theoretically should have happened is this. So they should have both grafted themselves on. And once they grafted themselves on, R4 should have grafted itself to R7 and so on and so forth. And now the traffic starts flowing. So here comes the ICMP traffic. R4 has both of these interfaces in forwarding, so it's going to send it out both of those interfaces. Both of the last hop routers have received IGMP requests, and that I just need to show you really quick here. They both should have received that IGMP membership report. Do show IP IGMP group. So there we go, there's an up reporter. And on R6, do show IP IGMP groups. There is an up reporter. So because the report is multicasted out, both of the last hop routers receive that report. Because they receive that report, they're both going to forward the traffic. So finally, they both forward it out onto this LAN interface. But when they forward it out on the LAN interface, they actually end up sending the traffic to each other too. So remember, now for this traffic, there is going to be RPF failure. So let me move all of this out again. And let's just talk about this traffic. So going from R5 to R6 and coming from R6 to R5. Now both of these interfaces, if you look at the source, it's still 1.10 on both of these packets. So that means there's an RPF failure here and there is an RPF failure here. But remember what you do with RPF failure on multi-access interfaces. You run the assert mechanism. So they should have both now sent an assert packet to each other. And based on the assert packets, so the assert packet contains what? It contains the metric preference. It contains the actual metric. And it contains the outgoing IP. So it's not visible here, but the outgoing IP. And one out of those has to become the designated forwarder. And in this case, I'm assuming that the metric preference for both is 110. We are using iOS and OSPF. The metric for both should be same. They're equal hop counts away, and I haven't made any changes. So this should be equal. That means the designated forwarder was the highest IP, which .6 is the highest IP here. So let's take a look at this on the packet capture if we can actually find it. So on the packet capture, I'm actually going to say pim.type assert. And I've lost the packet capture, so give me 1 second here while I pause the video. So I wasn't able to catch the initial asserts, but remember that flooding and pruning process took place again, so we had another assert. We had the same situation arise again. So if I look at it here, R5 was in pruned state. So R5 was pruned here and R6 was actually being forwarded traffic to. After that 3 minutes, this moved from pruning to forwarding. So there was traffic here, that traffic once again went to R6. R6's traffic went to R5, and there was assert one more time. So the assertion process took one more time. And this is that particular assertion process that we're looking at. So here we go. R6 sent a message to R5. And if you look at the PIM option, here is the metric preference. So metric preference of 110 and a metric of 5. So that is what is R6 telling R5, that I have a metric preference of R110, administrative distance, and a metric of 5. What is R5 saying to R6? Well, metric preference of 110, metric of 5. So that means the tiebreaker here is going to be up in the header. So 172.26.56.5 versus 56.6, and that means 6 won the assertion. And what 5 should then do is it should also send a prune. What was it, 3, I think? Yep. So after the assertion was won, 5 actually pruned itself, number 1, from that particular VLAN. So it'll send a prune message. So once the assertion takes place, R5 will send 2 prunes. So it sends a prune to R6 to tell R6 that, hey, we're not going to do this anymore. I've lost the assertion and it's your network now. You can forward traffic. But now, because there is nothing left in the oil, the last interface in the oil is now pruned. So it's also going to send a prune back to R4. And R4 is then going to prune this interface. So that is that second prune that you see here. So that first prune after the assertion is going on VLAN 56 to prune, to essentially tell R6 that yes, you have won the assertion and you should be forwarding traffic to this VLAN. I won't do that anymore. And then a prune sent to VLAN 45, which is to router 4, telling router 4 to prune that interface back. And if I look on R4, my steady state should once again be the same. So I should have pruned the interface going towards R5. Now, sometimes, especially in cases like CCIE labs, they may ask you to change the designated forwarder here. So there is, if you just follow the regular path, the designated forwarder almost always is going to be R6. So this is going to be the DF by default. What if you wanted to make R5 the DF? Well, there's a couple of things we can do. Well, we can change the metric preference. So we can raise the metric preference of OSPF as a whole. We can change the metric. We can make the metric a little bit better, maybe change the link speeds or something like that. Or maybe we can change the IP address. So those are some of the methods available to you. Let's try to use the metric preference here, or the administrative distance, right? So that would be one of the ways to do this. Now, I haven't tinkered with OSPF metric distances in a while, or metric preferences or OSPF ADs. So let's take a look at how that's going to work. I believe it is still the distance command. And what are we changing the distance? So distance OSPF, I believe that is for large route type. So that's not something we want to do. We want to change the distance for a particular route. And I want to change it to 109. That's all I need, right? 109. And the source IP address here should be the next hop router, I believe, or the router ID of R4. So that would be 172.26.0.4. It's using the loopback. And then the wildcard bits. How about 0000? And then the list would actually contain the IP. So let me just change the distance for everything that's coming from R4 to 0000. Let's see if that works. Do show IP route OSPF. Nope, that distance is, yeah, there we go. So anything that was originated from R4 has actually gone down to 109. So I know what I need to do here. What I need to do is not this command. who is advertising this route in my domain? So this particular route is being advertised by R1. And if I say do show IP OSPF database, here's R1. So what I need to do is apply the same command, but for R1. And that's one of those arcane things they may have you do in the CCIE lab. No matching address. Oh, because I'm using the no command here. So distance 109, do show IP route OSPF. And now you can see 226.0.0.1 is at 109. And 126.1.0 is also at 109. So that's the route that I wanted. So if I say do show IP route 172.26.1.0, now I can actually see that the distance here is 109. We will have to wait for that assertion to happen again. But let's see what was sent in the last assertion. Look, the metric preference is now 109. So now in this particular assert, because of our changing the distance, and I believe this is a triggered process. So as soon as I changed the administrative distance or the metric preference, essentially R5 should trigger an assert message, and it triggers this assert message over to R6. This time the metric preference is 109, and 109 is better metric preference than 110, which is what R6 should have been advertising. So R5 should now be a clear winner and a DF. R6 should now prune this interface, prune this other interface up this way. So let's see if that has happened. And R5 may need to graft itself back as well. So let's take a look at R5. Do show IP M route 239.1.1.1. And there we go. Now we are actually forwarding on that group. So we are forwarding on that VLAN. So VLAN 56, we are actually forwarding on it. And we are the assert winner. And that's why we are forwarding, because we are the assert winner on that particular group. R6 should no longer be forwarding on it. Do show IP M route 239.1.1.1. And now this has lost the assertion, so it has actually pruned itself off. On R4 now, remember R4 had 46 in forward and 45 in prune. That should now reverse. So now we should do show IP M route 239.1.1.1. And now you can see it has flipped. 45 is now forwarding and 46 is now pruned. There was also some grafting that must have happened back there, and the source, it's still sending all of those pings out. So far, just to recap, we have discussed how the packets essentially just flood on the neighborships that have been formed on the PIM routers. We've talked about the prune back. We've talked about how the routers, when they have an actual receiver, they're going to graft themselves back. And we have talked about the assertion process. Now, also for the asserts are, I'm not showing it here, but the asserts are also happening here. And they have a chance of happening up on this particular topology up here. So R2, remember, sends the packets down to R7 and sends them to R3. R7 should send them to R4, and R3 should send it to R4. But when R3 sends it to R4, remember, it's a non-RPF interface. In addition, R4 should also be forwarding a packet back to R3. So in normal cases, now, and this is the non-RPF for R3, in a pure point-to-point link, there would just be pruning that happens here, right? So just be pruning. But remember, this link by its nature is a multi-access link. And because of that, there would be assert here followed by the actual prune. So there would be an assertion that happens there, and that should be followed by the prune. I'm not sure if in a steady state we are actually going to catch this on the packet capture, but let's try anyway. Let's see if there are any other asserts. So yeah, it looks like in a steady state, yep, there we go. So there's 4 and 3 trying to assert each other, and then they prune each other's interfaces off. So that's also, you have to keep that in mind anytime you have multi-axis links that are essentially acting as point-to-point links. So that's very important there. The last part here that we have to cover is that of the state refresh. So let me bring those ICMPs back in here. So ICMP.type, right? That should be the echo request. And that actually is again crashing my Wireshark. So give me one more minute, I'll pause the video here. So what I will do here, now in the steady state of this, remember there's flooding going on all the time. So let's take another routing, another group, and let's ping to this group. So we'll say ping to 239.1.2.3. Why not? And nobody's listening to this group right now. What should happen every single time is that there should be 1.2.3. There should be this flood of packets going all over the place, and then there should be this join prune happening. Flood of the packets and join prune happening. Now that other flood that you're seeing is on that very first, between the first hop router and the source. So let me eliminate that out. And now that's eliminated out, you can see in the core of the multicast network, you actually have this flood of packets followed by the join prune. And this is going to happen every 3 minutes. The reason those states are there are because of the graph messages. So the states need to be there, especially on these last hop routers, if you think about it. So if I say do show IP mroute 239.1.2.3, it really needs these states here in case it got an IGMP join. So in case it got an IGMP report for this group, so on here, an IGMP report comes for this particular group, it needs all of this information and really all of the information here to send those graph messages. And that's why we keep the state here, and that's why we keep refreshing the state. Remember those timers? Via a flood and prune, just so these states are always there on the routers in case those graphs need to happen. So it's a detrimental thing, but there's a scaling issue here on 2 points. There is this much state. So if there were, say, 1,000 groups, there would be 1,000 states, star comma G's and S comma G's on every single one of the routers. If those 1,000 had another, say, 500 groups, then you're now working into permutations and combinations of how large those states are going to be in the state tables. In addition to this part, it's a necessary evil. I cannot get rid of the state information at all. The other part that is happening here is this flood and prune. This flood and prune, though, so once again, it has happened. It should be going up right now in a little bit here. So let me see how much time is left on this. 23 seconds. So in about another 23 seconds while I'm talking, you'll see there would be another flooding request to keep those states fresh. So that flooding, depending on how much bandwidth the source is actually sending at, how many sources are there, that actually is costly bandwidth that is going away to this flood and prune process all the time. So let me see. Well, here it comes. So here's another batch of the floods, and then it is pruned back again. So flooding, pruning, flooding, pruning. I cannot do anything about the state information. I need that for the graph messages. What I can do about the flooding is I can actually refresh the state using PIM. So all I need to do, all that flooding is really doing, the unnecessary flooding, is refreshing these states, right? So it's refreshing these states. And what I can do is I can use a PIM enhancement to refresh these states. And that PIM enhancement is called state refresh. There's 2 things involved with it. So first of all, you need to make sure that you have state refresh option signaled in your hellos. Now we saw that the Cisco routers are doing this by default. The second thing that we have to do is we need to make sure the FHR is configured to send these state requests for all of the active sources. So if it has an active source, it needs to be configured to send the state refresh message down the tree. And what is going to happen here is it's essentially going to generate that message, and it's going to happen on the first hop router. And it's going to send that message down the tree. It's almost similar compared to that flood and prune, but it's a single message instead of a batch of messages. It can be sent more frequently because there is less bandwidth involved with it. So you don't have to wait 3 minutes. You could actually send it a lot sooner. If you look at my lecture on it, it also has that prune interface and override and everything else. So you can actually pass state information from router to router as to what I think your state should be. So essentially the upstream router telling the downstream router what the upstream router considers the downstream router's interface state to be. If it's pruned on my end or if it's not pruned on my end, if I need to prune it. All of that information that the flood was actually carrying can now just be carried in a simple message called the state refresh message. So, and then it's going to go all the way down, and then the prune can happen as it would happen in response to a flooding. So now let's go ahead and quickly configure this. It's a single command on the interface that is facing your source. So this particular interface here, this is where that command would go. So this is where you would configure this state refresh. So let's go ahead and quickly configure that. On R1, I'm going to go to intg00.1. That is the interface facing my source. And I'll say IP PIM State-Refresh. Now I need to pick an origination interval. So how fast? I believe the actual origination interval, the default, I'm not a big fan of defaults, but I believe it's about 60 seconds or so. In order to bring this lecture to a quick close, let's refresh every 30 seconds or so. So now every 30 seconds, let's also look for that state refresh message. So pim.type equal to state refresh, I believe. Nope, or equal to state refresh. So right now, I don't think I've seen any state refreshes yet, but in about 30 seconds or so here, I should start seeing a state refresh go out. There we go. There's the state refresh going from router 1 to router 2, router 2 to router 7, up to router 4. Router 4 is going to send it on its forwarding or pruned interfaces to R5, and also R3 is getting, or R3 is actually sending one of those state refreshes. So let's take a quick look at what is actually carried in here. So I'll take a look at the very first hop here, which is R1. And R1, so number one, what is the destination of the state refresh? You want to refresh all of your neighbors on the multi-access interface. So the destination here for the state refresh message is going to be PIM. So 224.0.0.3, you want everybody to hear this. Type 9 for state refresh. Which group am I actually refreshing for? So what is the S, G? Who originated that group? This is always going to be 0. I've been told that this was for compatibility reasons with the previous version. So again, I'm not really sure what happens there. The metric preference here, this is exactly what would be in an assert message. So it's also playing the role of that assert message. And in this case, it makes sense, right? This is a directly connected link. So the metric preference is 0. And the metric is 0. So if we look for one other one, so let me look at something that R5 is sending over, which is right here, 56.5. Now you can see it's the same thing as the assert message. So the metric preference is 109, which we had changed, and the metric is 5. The next thing, once again, I have been told, I've never actually seen it the mask length anything but 0. And finally, there is a TTL. So you want to know how far that state refresh message has traveled. And this was for something called multicast scoping. So multicast scoping, you can actually look at the TTLs and see how far are you going to actually let this message travel. And then finally, the interval, which has been set to 30. Also, there is prune indicator. So whether you've received a prune from other interfaces on here or not. So if you remember, R5 got a prune from R6. So it's essentially telling everybody else that, hey, I'm the assert winner and you need to prune your interfaces. But as a result of this, what we should see every 30 seconds on the routers is every 30 seconds we should see that the state goes back to forwarding, so a prune state. Let's look at a prune state. Every 30 seconds, this timer should really, this expiration timer every 30 seconds should go to 3. So let's take a look at this. 247 right now goes down to 243, 241, 239. It should be receiving that assert soon. 233, 32. I want to actually see it happening. There we go. So it was all the way down to 230. It should have received that assert message, and just half a minute later, it got the assert message and re-upped that timer to 259. Normally this would happen every 3 minutes with the flooding, but right now it's happening every 30 seconds with the state refresh message, which is a great enhancement. But ultimately, if you look at the scalability of this, everybody still has those states, everybody still needs to keep those states. And that is what really makes dense mode very, very unscalable for anything but the smallest topologies. That brings us to the end of this dense mode lecture on iOS routers. If you have any questions, any comments at all, feel free to leave that in the comments section for the video. Other than that, I hope you've enjoyed this lecture and have a nice day.